Okay, today let's talk about other computational methods. So we already talked about the variational method and Hartree-Fock. Today is kind of a catch-all for the rest. So here's a screenshot from Gaussian. These are all density functional theories. B3LYP is the one that is probably best known and used. These two are perturbation theories. I'm not going to talk about coupled cluster theory. Those are a little more unusual. These are semi-empirical theories, and then it's hard to see here, but the UFF mechanics is a flavor of what's called molecular mechanics. So let's take a look at perturbation theory first. This actually comes up in a lot of contexts in physics, not just in quantum mechanics. And like I said, in Gaussian, the Moeller-Plesset 2, MP2 and MP4 are perturbation theories. The big idea behind perturbation theory is you approximate the system that can't be solved exactly with one that can, and so you find an analogous system that you can solve exactly that's similar to the system you can't solve, and then you correct for the perturbation, the difference between the two systems. So this is kind of how it works. Let's say you have the true Schrodinger equation, h hat psi equals e psi, and of course you don't know e and you don't know psi. Then you can say, okay, well, I don't know how to solve this, but I do know that the Hamiltonian is equal to some unperturbed system that I can solve, and then the perturbation that I can't solve. So we call this h hat naught and h hat 1. And the h hat naught is the unperturbed system that we can solve. And the rest is then the perturbation. So we know that there is a Schrodinger equation for the unperturbed system, that everything is known. That's the unperturbed. Then we assume that the energy in the wave function can be expanded as a power series. So like a Taylor expansion. So then we could say psi n is equal to the unperturbed plus first order correction, second order correction, etc. Same thing with the energy, unperturbed, first order correction, second order correction, etc. And so then we can plug these expansions back into the true Schrodinger equation. So h psi equals h hat naught plus h hat 1 times the expansion in the wave function, and that'll be equal to the expansion in the energy times the expansion in the wave function. Now I'm skipping some details in the derivation, but it can be shown that the first order correction, in the first order correction, the true energy is approximately equal to the unperturbed energy plus the first order correction, which is the unperturbed energy plus an integral over the unperturbed wave function, sandwiching the perturbation in the Hamiltonian. And the beauty of this is everything is known in this equation. So we can get our first order correction here. There are some advantages to perturbation theory. One is it includes excited states. So unlike with variational theory where we could only look for a ground state energy, here we haven't specified. We can look at any excited state energy because we know the excited state wave functions. And there also is a systematic way, I haven't shown you, but there is a systematic way to include higher order corrections. You can imagine we have them all here in our Taylor expansions, and we could work with those to get higher order corrections. The disadvantage is real systems might not have good unperturbed analogs, and so then your results might not be that accurate if they're quite a bit different from a system that you can solve exactly. Alright, so that's perturbation theory. Here's an example. Let's say we have an anharmonic oscillator where the potential energy, this first term is the unperturbed system, that's a harmonic oscillator, and then we have third order and fourth order in the compression expansion of our spring. So then the perturbation is that third order and fourth order, but we know for example, the ground state wave function for the unperturbed system is this. I chose to do the ground state. We could also do an excited state. But the ground state is fine for just illustrative purposes. And I'm not sure that this is the exact same notation as Atkins, but our alpha here is k mu over h bar squared, square root. Okay, so the first order correction to the energy will just be the wave function, the perturbed part of the Hamiltonian, so this is h hat 1, and then the wave function again. And if you actually do this integral, it can be shown that, and this is part of your problem set, that the first order correction to the energy is 3c over 4 alpha squared. Notice the b disappears. That's because this is an even function, and this is an even function, and this is an odd function, and you're integrating from negative infinity to positive infinity, so that ends up being 0. Anyway, so then the ground state energy for the anharmonic oscillator is the unperturbed energy h nu over 2 plus this correction term. All right, you'll do that in your problem set, and you'll do another example too with a particle in a slanted box. Some other methods, some of these don't even use a Schrodinger equation. Density functional theory is very popular and is used a lot. B3LYP is the main example. This doesn't use a Schrodinger equation at all. You have the energy is a function of a function. And this rho at r, this is the electron density. So you think of the system as just a cloud of electrons. And then you integrate over all space, and you've got some operation. So this is a capital rho hat operating on rho, which is a function of r. And you can solve for the energy, and this is usually done in a self-consistent way, similar to what was done with the Hartree-Fock, where you come in with an initial guess of rho r, and then you actually, I think the way the theory works is you take a derivative of this with respect to the function and set that equal to 0, and so you're minimizing with respect to a function instead of a variable. So that's kind of weird. A function of a function is called a functional. It doesn't have to be an unknown function, but in this case it is, because we don't know the electron density. We don't know the shape of that cloud. But that's kind of a cool thing, and it works really well. Notice there's no Schrodinger equation in here at all. Another method is molecular mechanics, MM, for example, UFF in Gaussian. In molecular mechanics, you treat all the atoms as masses and all the bonds as springs, and you just do classical mechanics. So that's molecular mechanics. It obviously is not good for things like, you know, finding a spectrum or anything like that, because everything is continuous. But it is good for maybe optimizing a geometry, something like that. This is often used in tandem with ab initio. So, for example, you could use molecular mechanics for the solvent, where you have a lot of molecules, but then use quantum mechanics for the solute, where you have very few molecules. And then the last category I'll talk about briefly is semi-empirical. There's a long list in Gaussian, for example, AM1, PM3, and others. For semi-empirical, you replace some of the calculations with experimental results. So let's say that we know from spectroscopy the bond length or something like that for our atoms. We'll just put those in there and fix those, and then we'll do our quantum mechanics on what's left of the system. So maybe exactly where the electrons are and what the cloud looks like. But we'll leave the bond lengths fixed, for example. And there are some other things you can do using experimental results, where some of the integrals that you would have to do to solve the quantum mechanics rigorously, you don't have to do because you're using experimental results. All right, that's it for today.